Chapter 3 is about inference, and it's in 3 parts. The first part, part A, is on the likelihood. So let's jump right in. Let theta be a parameter to a density or mass function f, y, theta, describing a model for the data. So if we're thinking back to chapter 1, theta was a proportion parameter in a Bernoulli model for coin flips. In chapter 2, theta was actually a vector of 2 parameters that are real valued and positive real valued respectively for a Gaussian model for the data. In this chapter, I'm going to focus on the Gaussian case. I should say for this vignette, I'm going to focus on the Gaussian case. The chapter has examples from both chapter 1 and chapter 2. But to keep the video kind of compact, I'm going to focus on the harder one, which is the Gaussian case. In chapter 4, we'll come back to the Bernoulli case. Okay, the likelihood is an expression of the joint probability of all n observations viewed as a function of the unknown parameter. Okay, so let's write that down. Here's a definition. The likelihood, underlined, is the joint probability of all of the data. So I'm thinking n observations viewed as a function of the unknown parameter. Now I'm using parameter singular with value theta, but actually I'm going to be doing an example with multiple parameters where theta is the quantities mu and sigma squared in the Gaussian example. Okay, so generically, what I mean is that the likelihood is a function of the unknown parameter theta through the joint density of the observations. And if we have IID data, this joint density is really a product of individual densities for that parameter theta. The value of theta that maximizes the likelihood so in math, we might write that as arg max, which is a fancy way of saying the argument theta that maximizes the likelihood is notated as theta hat, and this is the value that maximizes the likelihood. So that's the MLE, the maximum likelihood estimate. And this is the same as the value that maximizes the logarithm of the likelihood because of critical points and calculus, and the notation that we sometimes use for the logarithm of the likelihood is lowercase l of theta. Okay, let's do an example. Suppose that we have Gaussian data. So our parameter theta is really mu and sigma squared. And we have n of these observations. We already know from last time that the joint density, given these parameters mu and sigma squared, is a product of these densities. Sorry, I'm on. So the likelihood, which is going to be viewed as a function of these two parameters, can be expressed as whatever we choose to simplify this expression. So last time what we did was we wrote the 2 pi sigma squared part out front, and then we brought the product into the exponent like that. So I haven't really done anything that's different than what I wrote down in chapter 2, but now I'm calling it the likelihood because I want to think about it as a function of the unknown parameters. And if I take the logarithm of that and call it little l, then I've got a part of it that's got a minus n over 2 log 2 pi, but I'm just going to call that some constant c because it doesn't involve either of the parameters, mu or sigma squared. And then I've got a part of it that involves the logarithm of sigma squared. And then I've got, the nice thing about the logarithm is that it cancels this exponent and brings everything down, which makes it much easier to work with. Everyone's always like, why you got to do logarithms? This is the reason to do logarithms. It turns this big product into a sum and gets rid of the exponent. And the c is really just the 2 pi minus n over 2 log 2 pi, which doesn't have anything to do with mu or sigma squared, so it's kind of irrelevant from the perspective of an analysis of the likelihood, which is really all about those parameters. Okay, now how do we maximize the likelihood? Well, we do it one step at a time. So now consider estimating mu via maximum likelihood estimation. So let's look at mu. How do we maximize this log likelihood with respect to a parameter like mu? We use calculus. We take the derivative of the log likelihood with respect to mu, and that derivative is, we just need to look at this, and the c doesn't involve mu and the log sigma squared doesn't involve mu, so the only thing that involves mu is the third term with the sum, and it's a quadratic, so I'm going to get a 2 coming down, so I'm going to get minus 2 over 2 sigma squared sum, and then yi minus mu. The squared is going to become a power of 1 with a minus 1 in front from the chain rule on the derivative of minus mu. We set that equal to 0, right? To maximize, we take the derivative, set that equal to 0, and solve. I really have n mu's, and I have the sum of yi. So I've done a bit of simplifying by bringing the minus mu out front. There are n of them, and then summing the y's. The 2's cancel, and I can multiply both sides by sigma squared. multiplying sigma squared by 0 is just 0, and multiplying by sigma squared on the right will cause that sigma squared to cancel. It's customary to put a hat on the mu at this point because this is the value that you're going to solve for. And if you look at this closely, what I really have is a positive n times mu hat on one side, and then I've got a sum of the y's on the other, and I can divide both sides by n, and I get my answer. So mu hat is the sum of the y's divided by n. Okay? And of course, that's the same as what we've been calling yn bar. We called it that back in chapter 1. So it's the average. The estimate of the mean is the average. That makes sense. Okay, now consider estimating sigma squared. Via MLE. Same thing. Take the derivative of the log likelihood with respect to sigma squared. Got to go back to the log likelihood before we started taking derivatives with respect to mu, and then take derivatives with respect to sigma squared instead. Be careful, we're not taking the derivative with respect to sigma, we're taking the derivative with respect to sigma squared. So treat that sigma squared as a single quantity, as if it were like an x, and work with it, or with x, everywhere in the expression. Okay, so the minus n over 2 log sigma squared has a sigma squared in it. Taking the derivative of the log, we'll put a term in the denominator. So I'm going to get minus n over 2 sigma squared from the first part. The second part has sigma squared in the denominator already, so I'm going to get an extra copy of that. So sigma squared squared, and then the rest of the sum is going to come along for the ride. Oops. Okay, so that's the derivative. We're going to set that equal to 0 and solve. So now I can multiply through by sigma squared everywhere. I'm going to, multiply by 2 times sigma squared everywhere. So I'm just going to have a minus n here, and then I'm going to have a minus 1 over sigma squared there, and then the sum is going to come along for the ride. And again, at this point, I like to put a hat on sigma squared because that's the value that I'm going to solve for. And now this is pretty easy because I just need to rearrange a little bit by putting sigma squared in the numerator on the left, and then I'm going to get a 1 over n sum I equals 1 to n yi minus mu squared. And what value of mu should we use? Well, we solved for mu earlier, so we could just plug in the value mu hat that we got from before, and that is our estimate of sigma squared. So that's the MLE. And remember, this mu bar is mu hat is y bar n, so it's the sample average. One downside to this estimate this MLE for sigma squared is that the expected value of sigma hat squared is equal to n minus 1 over n times sigma squared. So it's not equal to sigma squared. So it's said to be a biased estimate because its expectation is not equal to the parameter of interest. There's a little bit more on this in the book, I'm kind of glossing over it here. But you can correct for that if instead you take 1 over n minus 1 times yi minus y bar squared. So that's the same formula as for sigma hat squared, but dividing by n minus 1 instead, so that when you take the expectation, the n minus 1's cancel. That is unbiased. And it's known as S squared. Okay, so this is an unbiased estimate. So this is generally preferred. And that's what we will use primarily going forward. So S squared is an unbiased variation on the MLE. Let's go over to R and wrap up this likelihood section by returning to the data that we have from chapter 2. So these are the heights of women in my class. There are n of them. And we don't really need this value mu that we use in the hypothesis test. We don't need this for the likelihood section, but we're going to use it later when we go to inference in the next vignette for this chapter. Right now we just have our estimate, so the MLE for mu, that's going to be the sum of the y values divided by n, which we know is the same thing as mean of y. So mu hat is the same value. Careful here, R uses the command called mean, but this is really the average. The mean is unknown. The mean is mu, and that's what we're going to conduct hypothesis tests about. This estimate of the mean uses the mean command in R, but is really giving you an average. It's adding up the y values and dividing by n. Okay, what about the MLE for sigma squared? That is going to be the sum of the y values minus my estimate squared divided by n. So this is the pure MLE, but it's biased. Right? That's that value. We can instead divide by n minus 1, and this will be unbiased. And that is what we're going to call S, or S squared. S squared is really just the variance of the y values in R. So you can see that that's the same number. When we calculate it ourselves by following the formula, we get the same thing as when we call the var command in R. So var is giving you an unbiased estimate of the variance. Again, this is not the variance, this is an estimate. It's really an average of the squared discrepancy between the estimated mean, mu hat or y bar, and the individual variables y, divided by n minus 1 instead of by n. All right, that completes part A. Part B will be in the next vignette.